Today we are going to talk about machine learning for the AutFab error classification at the hierarchy system. The project has been developed by Philip Hallenberger, Philip Kunze, Maria Camila Lopez, and Aditya Shakya. This was done under the supervision of Professor Dr. Stefan Simons. In this project, a meaningful, practical, and an application-based use case for machine learning is identified, possible frameworks are evaluated, and the use case is implemented. Out of the possible use cases, a decision is made to implement the error classification using supervised learning. For a supervised learning model, inputs must have an example dataset, usually a vector of features, and a corresponding label. The model is designed to analyze the label data and learn to classify data. After the training of model is finished, it is able to classify a new set of data into defined classes. The station chosen for project implementation consists of several light grids, emergency stop buttons, and station monitor doors. When one of the safety elements is triggered, the PLC changes to a safe state and the motion controller is switched off. If this happens when hierarchy system is in motion, an error occurs which requires specific solution. This solution depends on the time of intervention. To simplify things, unloading is divided into three different errors. Error number 3 can occur during the motion time when the fork is shifted from the start position to under the pallet. Error number 2 can occur while lifting the pallet on the fork, and error number 1 can occur during the movement to deposit the pallet on the shuttle. To choose the variables which will eventually form the features of our classification model, we looked at the PLC program. The motion in the hierarchy system is controlled by a sequencer, and during the investigation it was found that errors were generated inside the sequence chain, which is represented as a function block in the PLC program. The function block is supplied by information from the sensors, station-specific data, and actuator interface. These I/O variables of the function blocks were picked up as preliminary features of our classification model. Initially, the total number of features used were 124, but after successive revision of the model, we were able to narrow down to the most important data variables. These selected data variables need to be fed in the training model in a systematic fashion, and it is needed that the data flow in the system is managed efficiently. There are two major parts in data management. First part is the data pipeline, which manages the flow of the data, and the second part is the data visualization tool. This tool was specially created to help the team in visualizing data and extracting useful features from the data generated by WinCC. In operation, both of these things work with each other. The data is generated by WinCC in the archival file, and as this file works like a ring buffer, the data from the archival file is copied to a data bank to avoid the loss of data. In offline operation, once the required data is recorded, the data bank file is translated from WinCC CSV format to standard CSV format. After the translation is done, it is then sent for data preparation. Once the data is prepared according to the classification model, it can be used for training model. To see this in operation, we need to start the visualization tool and then select Data, Convert WinCC from the menu, and choose the data bank file. Once the translation is finished, we can load the database by selecting File, Load Database. The loaded data can be viewed in the sample browser. For the visualization of data, we have two options: 2D visualization and 3D visualization. The left section of the tool is graphics part, and the right section has the control. In 2D visualization, features can be selected to define the two axes, and in 3D visualization, three features can be chosen from the control section to plot them in the same 3D space. This way, we can find the pattern in the data and find out the correlations between them. To find correlations, certain data variables can be added to the correlation plot. Here we can see that the two data variables are strongly correlated with each other, but the important feature moves forward is only correlated to this variable. We can also create histogram of the individual data variables. This can be done by right-clicking on any variable and selecting histogram. Now we see the distribution of the variable. Additional features can also be created in the tool. From the drop-down list, here the type of variable can be selected. The updated database then can be saved by selecting File, Save Database. To see the live classification model, we need to press the Do Not Press This button. In the live classification screen, we see the implementation of three different machine learning algorithms. The first chart shows the classification using decision tree. Here, the model tries to find if-else style rules to classify the data and create a decision tree based on these rules. The second chart is an implementation of neural networks. In this type of model, interconnected virtual neurons are organized in form of an input neuron layer, few hidden layers, and a final output layer. The input layer has the same number of neurons as input features, and the output layer has the same neurons as the number of labels in the data. In our case, output layer has 3 neurons as we are classifying 3 errors. The third model uses support vector machine algorithm for classification. This model classifies data by supporting a hyperplane on support vectors, which are nothing but data points of a certain class plotted on a multi-dimensional space. The number of dimensions in this space are equal to the number of input features. Effectively, this hyperplane cuts the data into different classes. Here, the live error classification is shown along with manual error creation. Type 2 error is being manually created by inserting a hand in the light grid. It can be seen that error 2 is correctly detected in all 3 types of model implementations. This is the result of our project. Thank you for watching.